My name is Trevor Edna Takaisa from Group MLSW24, and today I'm presenting the project under the title Real-Time Biomechanical Skill Classification for Bike Dispatch via Cloud Deployed Long Short-Term Memory Neural Networks. This is an overview of what I'm covering today. Road accidents involving bike riders has become a rampant safety concern, especially in Uganda, and these are caused due to the lack of skills by the riders, for example, moving from one lane to another or just simply navigating a corner. And so our system presents a solution where riders are able to demonstrate their competence by simply recording a demonstration and then evaluating the demonstration using our system to give a verdict whether the rider is a poor rider, average rider, or good rider. And this is done at the dispatch point before the bike is given. For related works, we have the media pipe pose, the study whereby just a lightweight 3D body landmark extractor that depends on clear video as well as good lighting, which we use to turn our video frames into simple joint coordinates. We have the LSTM, which is a recurrent neural network with memory cells for sequence learning that captures patterns over time and avoids forgetting the earlier steps, but basically requires sequential data and larger models that need significant compute. And in our case, we basically read 16 frames in order to judge the riding skill of a particular rider. For the biomechanics framework, basically rules for turning joint positions into meaningful motion scores like balance, which gives the physical meaning to raw numbers and needs adaptation for motion capture to pose-only features. This basically provides theoretical basis for our 7 interpretable biomechanical features. For the domain application problem, our smart rider assessment system is designed to assess the skill level of a particular rider based off a short video clip, and the system focuses on analyzing the bicycle behavior, riding behavior using the video data to evaluate rider skill and detect unsafe riding patterns. For computational problem, it involves automatically analyzing video data to extract the mechanical features of bicycle riders, and then using machine learning techniques to identify patterns in rider movement that distinguish the skilled riders from the unskilled riders. Our research question is, can unsupervised machine learning reliably differentiate skilled from unskilled riders using artificial biomechanical features? And for our objectives, it was in order to conduct comprehensive exploratory data analysis as well as assess rider skill level using the riders form. For contributions, we're able to get 2 data sets, RoboFlow dataset as well as the ACF1 dataset, which we use to produce a comprehensive visualization exploratory data analysis suite that systematically validates cluster quality. We built 8 models for our datasets and 2 compressed models techniques and deployed our best model and the best compression model technique. For our methodology, we basically identified a problem, obtained the 2 datasets, performed an EDA, trained the models, deployed the best model, applied 2 compression techniques, and we deployed our best compressed model. For the dataset description, we're basically looking at 2 datasets, a RoboFlow dataset containing still images of cyclists in varied environments, as well as the ACF1 dataset containing human action recognition, where I focus on the biking class containing videos of bicycle riders used to determine the behavior patterns, making the riders to make mistakes. Here we looked at 7 features: the balance, looking at the hip alignment, then the posture, looking at how the torso is aligned with the hip, confidence, clearly checking out that the media pipe can see the riders in the frames, the speed consistency, looking at how consistent the limbs of the rider are moving as the rider is riding. Upper body stability, basically looking at the position of the shoulders. Pedal rhythm, to look at how consistent the pedaling is over time. And last, the pedal symmetry, to look if the legs are moving evenly during the riding process. These are our evaluation results. These are our data results. From the EDA, we have the cluster distribution, where I basically look at the samples of the skilled as well as unskilled clusters after the media pipe pose detection, which you can clearly see skilled is greater. Then for the samples per source, we are looking at the number of samples within each data set after the media pipe pose extraction, and then clearly classifying these data sets into skewed versus unskewed individually. For the split distribution by source, we are looking at the number of samples present within each split under the two data sets after the media pipe post extraction. And below, we are looking at the number of post samples within the ECF class after the extraction, media pipe post extraction, and then clearly classifying the skewed versus unskewed under the Bioking class, which is under the ECF 101 dataset. For media pipe post detection rate by source, we are basically looking at the rate at which the media pipe was able to detect the samples that were within the two data sets, and we can clearly see that given how clear the data set samples were and the lighting within them, several samples were dropped, and so this greatly reduced our detection rate by source for the two different data sets. And then for the input versus detected samples, it is also relatively low for the detected as compared to input based off the detection rate by source. For the correlations, we are basically seeing how the seven features correlate within each other, and we see that the 0.88 is the greatest correlation between posture as well as upper body stability, meaning for posture to be good, then upper body stability has to be good as well. In this slide, you're basically looking at the score of the features to see which of the features can clearly distinguish among the three skill tiers we have, and we can clearly see upper body stability and posture have the highest score, followed by the pedal rhythm, the balance, as well as the pedal symmetry, which are also able to identify or clearly distinguish among the skill tiers. This is the class distribution of the sequences extracted from the frames generated by the videos, and then there is a clear balance here among the class distribution for the ECF 101 dataset, where we have 33% for both poor and average and 34% for good. And this one basically just looks at how each feature performs in the skill tiers. This also looks at how each of the features is able to perform under the poor, average, or good. And here we have posture and upper body stability clearly being able to distinguish. Here we also look at how the classes are able to distinguish among the three classes, and we see balance is really good, as well as the upper body stability. They can really distinguish among the three. We move on to the model architecture, and the first one is the K-means clustering out. K-means, we basically take 7 biomechanical scores per rider and place 3 centroids in the space. We assign every rider to the nearest centroid and recalculate the centroid and repeat until the centroids stop changing. So the 3 resulting clusters are then ranked by the composite score we have, and then we are able to map the clusters onto poor, average, or good. For the second model, we have the DB-scan, which is the density-based spatial clustering of applications with noise. This one basically identifies clusters as regions of high density and assigns regions of low density as the noise. So we take the 7-feature matrix, and for every rider, it looks within the radius called the epsilon to just find the neighbors. So if a point has enough neighbors, it becomes a core point and starts a clusters. Points that are near then get pulled into that cluster, and any rider too far from any cluster is labeled as noise, meaning that that they cannot be evaluated or classified. So the remaining core point clusters are ranked by the composite score and mapped onto the poor, average, or good skill tiers. Moving on to the agglomerative clustering, here we start by treating every rider as their own cluster, which leads to very many clusters. Then we repeatedly merge the 2 closest clusters using the word linkage and repeat until only 1 cluster remains, and then we cut our dendrogram at k is equals to 3, leaving the 3 groups ranked by the composite score and mapped onto the poor, average, or good skill tier. Then the Gaussian mixture model basically just initializes the 3 Gaussian components, alternates between computing how likely each component generated each rider's data in the E step, and then updating the component shapes in the M step, repeating this until convergence. We then flag any rider who is below the 70% confidence as borderline, and then map the remaining soft assignments to the skill tiers, good, average, or poor. Moving on to the models that were trained on the ECF 101 dataset, we start with the SVM, which basically just takes 16 frames with 7 features scores each, and then flattens them into 112 values, which normalizes them with like the standard scalar. Then the radial basis function kernel then maps these 112 values into a higher dimensional space, where the classes then become linearly separable. In this case, only 3 classes are then becoming linearly separable, drawing the boundary that maximizes the gap between the poor, average, or good. For the graphical neural networks, we basically treat riders' bodies as graphs with 33 joints. And then across the 16 frames, we are able to add temporal edges connecting each joint to itself in the next frame. And the 3 attention layers let the joints communicate and build full body understanding. Then pooling summarizes them into a single verdict of good, average, or poor. Moving on to the 3D convolutional neural networks, this one basically just processes all the 16 frames at once as a volume, and then each convolutional layer learns increasingly complex patterns from the basic edges to full cycling coordination. So a global pooling then finally summarizes the movement patterns into one vector, and the dense layer outputs the skill tier as good, average, or poor. Lastly, we have the long short-term memory neural network, which is our deployed model. And this one basically just treats 16 frames sequentially, one at a time, maintaining memory of what it saw before. So the 120 unit layer, which is our first LSTM layer, just captures the full motion pattern. Then the dropout layer prevents the overfitting. Then the second LSTM layer, which is the 64 unit layer, compresses it into summary. And then the second dense layer then outputs the 3 possibilities as good, poor, or average. These 2 tables are able to classify our 8 models, and the score for each, where we have the supervised classification model as well as the unsupervised classification models that have the different scores, as well as in the supervised, look at the accuracy F1 score, as well as the standard deviation, and in the unsupervised, we look at basically the silhouette score, the DBI score, as long as the CHI score. After training our LSTM neural network model, we faced a challenge where our model had very many parameters, which were manageable on a server but heavy for mobile devices. So we did the knowledge distillation first. And here we had layer 1, where we had each frame from the 7 features projected to 32 dimensions. Then the frames talk to each other, which led to different types of relationships. Then we're able to add the original input back to the attention output. Then the layer normalization stabilized values. The layer processed each frame independently to refine the mixed representations into useful features. We're then able to add the original input back, and layer normalization stabilized the values again. And after each frame had been enriched with data from the other frames, the layer then collapsed into a single summary, which narrowed down to 3 possibilities of good, average, or poor. This table summarizes the parameters we had before, as well as the accuracy that was maintained, which was good. For the model compression technique number 2, we had pruning, whereby here we basically just remove redundant low magnitude weights to create a sparse model. And so we used the accuracy prediction accuracy of greater than 95%, which when met was safe for a method to be deployed. We had 3 methods, A, B, and C. At A, 50% of all the weights were removed at a go. And here, the size significantly reduced, then the accuracy remained at 49%, which made it not to be deployed because it did not pass the prediction accuracy. Method B, all 70% of the weights were removed at a go. This greatly reduced the file size, then the accuracy became too low, and then it could not be deployed. And it is only deployed in a point whereby the size is what is considered as compared to the accuracy. Method C was basically just gradually removing weights in 5 rounds at a time, removes the weights, retrains, and then removes other weights and then retrains. This was able to maintain the accuracy of 95%, but then reduced by only 7.9% as the weights were being restored after the retraining process. So because of this, the best technique to use was the knowledge distillation techniques, it maintained the accuracy and also reduced the file size. This table shows the sparsity, zip size reduction, as well as the prediction accuracy of the three methods. The deploy pipeline had 4 layers. The development layers were developing our code on our machine and storing the code and everything. For the build layer is where we're basically defining the environment using the Docker file. For the cloud layer, we had 2 spaces, the API space where we're running the Docker file, as well as the UI space, whereby we're running on the browser to see what was happening. The user layer is what is going to be explained in the next slide. Here, we basically upload our video, we press the analyze button, then we're able to get a verdict, as well as the score of each of the 7 biomechanical features, and then get coaching tips. Finally, the system is able to differentiate between the skilled and unskilled riders based on the features, and posture, balance, and upper body stability greatly affect the rider's movement. We had data set constraints, especially in relation to Uganda, and our results may vary from expert cyclist analysis, and also low detection rates by the media pipe due to bias towards cleaner and easier samples. We aim to collect Kampala-specific data, including images as well as short clips, as well as work with expert cyclist coaches to validate our results and target actual bikes, clothing, and environments used locally in Uganda. Lastly, we would like to offer our heartfelt gratitude to our supervisor, Dr. Galiwango Marvin, for his guidance in the course of this presentation and the course of this project, and offering us guidance throughout the course of this project. Thank you so much.